Josh had to leave early. He had a bit of an emergency. So I'm Tabbetha Dobbins, and I'll be presenting along with Yuanning Feng and also along with Nate Colley. But the rest of our group members, Miquel, Steve, Yunyan, and Josh, and as well, we benefited from all that we learned from the other workshop teams in the big open session about nanofluidic bearings. So these might be important in reagent delivery systems. These are nanofluidics. They might be important in forensics in terms of accumulating the reagents that we're interested in, infiltration, and of course, all of these fall into the class of bioanalytical chemistry or analytical chemistry. The concepts come from two key concepts. The work by Stoddard and Zink, where they had a photo-switchable set of motors inside of a set of channels, and these were published in nanoscale. It's sort of a little bit cut off. And so we combined these notions of having photo-activated motors along with the idea of having microfluidic channels, and this microfluidic channel platform shows you that you can sort of change the amount of length that the fluid has to go through, and so therefore you're changing the amount of resistance that the fluid has to go through, you're changing the volumes of fluids that land at the end, and also you can mitigate the timing for fluids in these channels. The one thing these channels are missing are any control systems that help the fluid flow better, and so that's what we're having a plan to design here. So here we have a 5 to 20 nanometer channel, we envision this to be, and then we would like to have the fluid flowing and be operating a Feringa motor, and so we can do this. We can actually have these channels positioned with charges, and the one key thing here that was added to the idea is to integrate into this the azobenzene. And this azobenzene is important because it can actually flip from a trans configuration to a cis configuration, and so you can envision a motor that would be going this way, and then after the light has hit the azobenzene, now the motor is flowing in this direction. So we position it right down here, right below the Feringa motor to change its direction, and this is really what's actuating the fluid. So we think that there are a set of barriers that we had to really overcome in order to make this a reality. The motor geometry and synthesis, really how do we precisely position these motors down inside of channels? The choice of the channel and substrate, so these are two examples. These are anodic alumina. You can make these down to 20 nanometer in size, and these are meta-organic frameworks, and these are typically pore sizes and channel sizes that are about 5 nanometers in size, but they are organic molecules that we can then address with organic chemistry to attach the motors. It's important with this type of a technology to have an alignment of the motors as well as to have them sort of synchronized in their actuation. And so we're thinking that for alignment we can do substrate anisotropy, linker anisotropy, or fabrication, different fabrication techniques. And the final fluidic designs, we have to worry about the scale where this might work out, the channel design, and how many motors we should put per unit length along our
Thank you.
channel.
So in order to overcome some of these barriers, we have a crude design of a Feringa motor. So in our motor design, we have this longer attachment on the top with the hope of moving solvent or fluid more effectively. But how it's drawn, the motor would just move this way, like vertically. So in order to make it flow or push solvent fluid in the correct direction, we introduced this azobenzene as an asymmetrically as one of our anchors. So whenever we hit that with UV light, it'll tilt the motor itself. So now you can imagine the motor moving this way, and if we can align them somehow onto a surface, we can have control over, like bulk control over all the motors to get the flow in the direction we would want to. And again, I just have that showing here. In this A2 anchor is showing the azobenzene. But again, that's one of the challenges. So we have a few different strategies to attach a linker like that onto a surface. So the first being taking advantage of an electric field. So if we could somehow have an electric field to selectively So having two different anchors have an electric field to selectively put the anchors down so that they're all going in one direction, all the motors. Another way would be to have asymmetry in the linkers itself. So if we could have the anchor selectively bind the surface in one part and the other anchor bind in a different part. And the third way would be to, if we just take advantage of equilibrium constants, so say one linker could bind to the surface at a higher rate than the other, then we can force that asymmetry, and also we can take advantage of that just by flowing our whatever solvent we want to begin with. So the flow would also help us to anchor those substrates down selectively like that.
Okay. So what kind of device characterization and performance we can work? First is about the test accuracy. For example, different kind of light power may affect the motor speed or something like that. And also the anisotropic excitation and flow choice may also be very important about what kind of plug we will use for such molecular motors. Also, we will test the geometry, for example, the pores, and also the microfluidic properties. And motor's functionalization is also important. We can design different kind of motor to see if it can work perfectly in the microtube. Also, I would like to point out about the scientific benefits, the collective behavior, and this can be applied to other technologies. For example, the NEMS, which is nano electromechanical system, and the micro electromechanical system. Example of an active surface. And also, it can test about the mechanical trapping materials, shear the surface, and nano positioning. For example, studying the non-Newtonian fluids, we can see if it can work in such a microtube. Otherwise, we may ask the question, can we reduce the scale to the single molecular delivery? We can think about the size of this molecular motor can work, because it's probably one of the tiniest motor in our world. Eventually, the nanofactory to get a single molecule in our system. So we also think about the potential funding resources, for example, the NIH and the NSF, which because our project can talk about the nanomechanical sensors, nanofluidic system, and so on. We also want to get the funding from the DOE and also the CAST and Ford Motor company, because we may design the system that can benefit the patient as a next generation of automotive sensor and actuator and active wings here. And thank you very much. Welcome the questions.
Any questions from the judges? No questions? All right. Any questions from the audience? Okay. Yep.
So does the wavelengths to active the Azobenzene affect the rotation of the motor?
Yeah, normally it can, but we can also modify the motors to change the wavelength. You can make it different or the same.
All right. Okay. Cool. Thank you so much. Thanks a lot.